Lesson 3 of Part 1 of Magnetism. This is on uses of electromagnets, and we're going to start with a question that's doing a little bit of revision for Lesson 2. So it asks, use ideas from the last lesson to describe and explain in detail how the number of turns, the current, and the type of core affect the strength of an electromagnet. So to do this, we're going to go back and we're going to think about when we drew the magnetic field around a solenoid. So this is the diagram that we did the last time. So this is showing a solenoid with 4 turns. These symbols here show where the wire is going into the page, and this is where the wire is coming out of the page. And when there's a current flowing, it creates a magnetic field around each of the wires that the current's flowing through. So there's a magnetic field around this wire, around this one, and so on. And the first thing we can say is that we know that overall the magnetic field of the solenoid, we can find that by adding together the magnetic field of each of the individual wire when they're pointing in the same direction. So we see that all of these arrows are pointing in this direction, so all of these magnetic fields will add together. Now what that means is that so this one and this one and this one and this one are all going to add together, and they're also going to add to these ones. So if I add some more turns, what that means is I'm adding extra magnetic fields. So overall, I'm making my electromagnet stronger. What else can we do? Well, we can increase the current, and if we increase the current, what am I doing? I'm making these magnetic fields stronger. I'm making these magnetic fields stronger when I increase the current through each of these wires. So again, because they all add together, that will overall make it stronger. And the third thing I can do is I could put a piece of iron inside here. This is a magnetic material, and remember that was our north pole, that was our south pole. So what's going to happen is this is going to induce a magnetic field inside here. So this will add along with the magnetic field from the wires to give us an even stronger electromagnet. So we're going to put that into words. So there was a written answer given in the PowerPoint, which I've written in slightly different words here. So what I've said is the magnetic field of an electromagnet is produced by adding together the magnetic fields around each of the current carrying wires. So if we increase the currents, that increases the strength of these magnetic fields. So it also increases the strength of the overall magnetic field. Increasing the number of turns increases the number of wires, so it increases the strength of the electromagnet. And finally, if the core is made from magnetic material, the magnetic field of the induced magnet is added to the overall magnetic field. So in the next question, this is exactly a repeat of the question in the previous lesson. So it's again comparing the properties of the electromagnet to the permanent magnet. The things they have the same is they are both not induced magnets, that is, they have their own magnetic field. They don't depend on have there been another magnetic field for them to become magnetic. And they both behave like magnets, so they both have north and south pole and generate non-contact forces as usual. The permanent magnet, its magnetic field is always on, and the strength of the magnetic field cannot be varied. Whereas with an electromagnet, the magnetic field can be switched on or off, and the strength and direction of the magnetic field can be varied. And we can use these difference in properties to look at different applications for these type of magnets. Okay, so some typical applications are bullet train, or these are trains that are made to levitate above the tracks, and that way it reduces friction, so we can make them go much faster. They're used for sorting metals in recycling centres, for MRI scanners, which are used in hospitals, they're used in power stations, and they're used in loudspeakers. So I've given 5 typical applications for electromagnets. So for things like the levitating train, the magnet needs to be extremely strong. So we use an electromagnet because by changing the number of turns and by increasing the current, we can make it, the magnetic field, very, very strong. And that's obviously needed to overcome the massive weight of the train. MRI scanners also need very strong magnets. They're some of the strongest magnets that you might come across that are inside MRI scanners. And likewise in power stations where we need to generate very large voltages, we need very strong magnets. So for these three applications, the main advantage of electromagnets is that we can make them very strong. Sorting metals for recycling, so we need to pick up the magnetic material out of a pile of rubbish, be able to lift it away and move our crane somewhere else, and then drop that into that other location. So that allows us to separate magnetic material from non-magnetic material. So we need to be able to switch on the field to be able to pick up the material, and then switch off the field to be able to let go of the material. So we need an electromagnet to be able to do that, because the electromagnet can turn on and off. And with a loudspeaker needs to vibrate in response to a signal. So by turning on and off the magnet inside the loudspeaker very quickly, that means we can make the loudspeaker vibrate and hence generate sound waves. So in this example of using an electromagnet, the electromagnet is here, and we see that it's switched on and off and it's connected to this power supply. So when we switch it on, current is going to flow through this electromagnet, and that's going to cause this to generate the magnetic field here. Now that magnetic field is going to attract this bolt. This bolt is made from iron, and so it's going to be attracted to this electromagnet when it's switched on. But we can see that for that bolt to move towards the electromagnet, it needs to compress or squeeze this spring. So this spring is stopping the bolt from moving towards the electromagnet. So in order to compress the spring enough to allow the iron bolt to reach the electromagnet, we'd need to have a very large magnetic field, a strong magnetic field. If the bolt is moved, what we can see is the bolt is embedded into this plunger, and if the bolt is pulled out of the plunger, well, what's going to happen is here a spring is being compressed, and if we push the bolt this way, that spring will then move upwards and push the plunger upwards. And if the plunger moves upwards, we see the plunger is connected to the switch. So what will happen is the plunger will move the switch upwards, that will break the circuit, and there will stop being current in the circuit. So with normal current, the electromagnet produces a magnetic field and attracts the iron bolt. Why doesn't it move to the left? It doesn't move because the magnetic force is balanced by the force from the spring pushing the bolt to the right. So in terms of this bolt, if I drew this as a free body diagram, what I have is, this is my bolt, and I have the magnetic force from the electromagnet, so the force from the electromagnet, and here I have the force from the spring, like that. Force from the electromagnet pulling it to the left, and the force from the spring pulling it to the right. These are equal, so the bolt won't move. When the current increases, what happens to the magnetic field? So we saw this from our starter earlier. When the current increases, the magnetic field becomes stronger. And then we say, using the answer to question 2, explain what happens to the iron bolt when the current is increased, and hence what happens to the plunger. Okay, so when the current is increased, the bolt is pulled to the left because the magnetic field is stronger. As the bolt is removed from the plunger, it moves up, pushed by its spring. So as this is moved left, this is pushed up by the spring because the bolt is no longer embedded inside. What does the push switch do when the plunger moves, and what effect does it have on the circuit? Okay, so when the plunger moves up, the plunger is connected to the switch. This push switch also moves up, breaking the circuit. So current stops flowing. So remember what we were saying here, it's a circuit breaker, a type of switch that automatically opens. When we say a switch opens, this means that the current stops flowing. The circuit stops working if the switch is open. So the type of switch that automatically opens to stop current flowing when there is too much current, shutting off the circuit. So when the current's normal, the electromagnet is producing a magnetic force, but it's balanced by the spring, the circuit continues to work. But if the current becomes too large, this magnetic force becomes very large, so the iron bolt is moved, the plunger moves up, and the circuit switches off. Right, the second application, it's called a relay switch. It's used to control a circuit with a high voltage and current levels, which is dangerous, with a second circuit that uses low voltages and currents. So one example of this is in a car engine. So some of the voltages can be very large inside a car engine. So we use a circuit when we switch on the car engine with the key. That's using a low voltage circuit, and there is a relay switch to then cause the high voltage part of the circuit to work without us having to touch the high voltage part of the circuit. So let's see how this is working. So in the picture we have two circuits, circuit 1 and circuit 1. This is the low voltage part of the circuit, and voltage 2, this is the high voltage. So this is the part that we don't want people to touch. So what happens here is I can push this switch and switch on the low voltage circuit. So it says when the switch in circuit 1 is closed, the electromagnet closes the switch in circuit 2, the circuit 2 is complete. Analyze the circuit. Okay. Explain, so when the switch in circuit 1 is closed, current flows, a magnetic field is generated by the electromagnet. Explain what happens to the rocker switch when the electromagnet is switched on. Okay, so by closing the switch in circuit 1, current flows, so the electromagnet generates a magnetic field. Okay, so this magnetic field, and if we notice on the rocker switch there's a piece of iron. This attracts the iron contact on the rocker switch which rotates anti-clockwise. So what will happen, this part of the rocker switch is attracted downwards, and because the rocker switch is free to turn around this point here, as this is pulled down, it's going to rotate like this. So then, question 2, explain how the rocker switch closes the switch in circuit 2. So the rocker switch rotates as the iron contact is pulled down. This causes the switch to push contacts together in circuit 2. So that would then close this, close this switch because these contacts come together, so current will flow. Suggest how this relay keeps the person using the motor safe. So the person only touches a switch in the low voltage circuit 1. So even if there is a fault, the person will not receive an electric shock. So here they're working with low voltages with a battery or a cell, and because of that they won't receive an electric shock even if there's a fault in the circuit. But if they had to switch the switch here in the high voltage and there was a fault, then they could potentially make contact with very high voltages, which could cause them some injury. Okay, so those were 2 typical applications for electromagnets. And now the last task you need to do is to look at, once again, this typical experiment that we saw in the previous lesson. We have a student investigating the strength of electromagnets, and it shows 3 experiments that were done. So we've got 3 results with paper clips shown in the figure. We've got electromagnet A, B and C shown in these pictures. Write a conclusion for this experiment. Increasing the number of turns of wire wrapped around the nail will do what to the strength of the magnet? Well, here we have the circuit is the same in each case. We have one cell placed, so we have the same voltage applied in each case. In this circuit we've got 20 turns, in this circuit we've got 30 turns. When we've got 20 turns we've got 1, 2, 3, 4 paper clips picked up. When it's 30 turns we've got 1, 2, 3, 4, 5, 6 paper clips, and likewise here 1, 2, 3, 4, 5, 6 paper clips here. So when we go from 20 to 30 turns, we're able to pick up more paper clips, showing us that the magnetic field is stronger. So increasing the number of turns of wire wrapped around the nail will increase the strength of the electromagnet. The cell in electromagnet A is swapped around to make the current flow in the opposite direction. What is the maximum number of paper clips that can now be hung in a line from this electromagnet? Fewer than 4, 4, or more than 4. So this is what we see happening in here between this one and this one. We see that this cell is switched around and we've got the same number of paper clips being picked up. So when we have 30 turns, switching the cell around doesn't change the number of paper clips that we're able to pick up. Now, why is that, and what does this mean for electromagnet A if we switch around the cell? So we can say, by swapping around the cell, the current flows in the opposite direction but is the same size. So the amount of current doesn't change, it's just the direction that changes. So since the current size doesn't change, the strength of the magnetic field doesn't change. So we've got the same strength of magnetic field. Therefore, the circuits will pick up 4 paper clips as before. So when we swap around the cell, it means the current's going in the opposite direction, but it's the same size, so we pick up the same number of paper clips, which for electromagnet A, that was 4. And that's the end of lesson 3.